All right, we begin chapter 6. Chapter 6 involves a lot of geometry. Today we investigate the area bounded between two curves. We have two functions, f of x and g of x. What we would like to consider is the area that's bounded between these two functions. We've been able to find the area bounded beneath the function and the x-axis. What about the area bounded between the two functions? Carter was beginning to introduce that topic one day. Thank you, Carter. It looks like it would be very complicated because the base is not, a nice, straight line, okay? But it's really not that bad at all. And we start by drawing rectangles. Would you agree that the blue rectangle represents the height of f of x with a width of dx? Okay. And then I'll use a red rectangle to represent the height of g of x. Wouldn't then the green rectangle represent the height from g of x to f of x? So give me a geometric representation or some type of way of thinking about it. How would I use the blue, the red, and the green to come up with a relationship? Yep. Yep. And so, yeah. Yeah, exactly. So if you just take the blue rectangle minus the red rectangle, you get the green rectangle, correct? So therefore, the area between two curves becomes very simple. It's simply the area, a to b, whatever our bounds are, f of x minus g of x dx, where f of x is the top function and g of x is the bottom function. So it's very important for you guys to understand that it's not as though we just make these formulas up. I mean, we use very basic logic to come up with them. Is everybody okay with that idea? Question? Today, for the most part, but it does get more complicated. But we're actually then going to take this shape and revolve it around the x-axis. And we're going to come up with a volume that's so its shape is going to have kind of a gap in it. It's going to be, yeah, it's going to be really cool. Okay, so it's going to be a really good time. You'll be excited. So let's move on. Okay. We start by this. It says find the area bounded between y equals x squared and y equals negative 2x plus 3 over the interval 0 to 1. So that means x equals 0 to x equals 1. Okay? So we first need to identify kind of the space that we're working with. So x squared and then negative 2x plus 3. What does x squared look like? Negative 2x plus 3. Everybody agree that that's a general representation of the two functions? So which function appears to be on top? The line or the parabola? Okay, you say that the line appears to be on top. That would be if we drew the height right here. When I say draw the height, I mean you're drawing that little rectangle. So in that situation, it would appear the line would be on top. But in this situation, it would appear that the parabola would be on top, right? So it says we're going from 0 and we're going over to 1. It would be nice to know where 1 is, wouldn't it? So it would be nice to know that intersection point to verify that the line is for sure always on top. We could use a calculator, but we can do it by hand. Not too big of a deal. We're just going to simply substitute. We get x squared is equal to negative 2x plus 3. Yep. Very good. So Michael's factored that, and we have answers of negative 3, positive 1. So what that means is that this intersection point back here happens at an x value of negative 3. This intersection here happens at a value of 1. So from 0 to 1, is the line always on top? Yes. And we'll pick up there when we get back. Go get some brain food, folks. See you in a little bit. Okay, as you look at this graph here, would you guys agree then that the shaded area sits between 0 and 1? So what's always on the top then? Yeah, so we have negative 2x plus 3 is always on top, and on the bottom is going to be x squared. So therefore, the integral becomes 0 to 1 of negative 2x plus 3 minus x squared dx. Antiderivative of negative 2x plus 3x minus x cubed over 3 negative 1 plus 3 minus a third minus 0. 2 minus a third, so 6/3 minus 1/3 is 5/3. That's your answer. Some people ask about checking your answers. Well, there's really no way to do it. That's what's challenging about this. For example, I could take this and plug this into my calculator and see that I do get 5/3. But how do I know that this is correct? You don't. You really got to make sure that you've set it up correctly. You have to know the bounds. You got to be confident that your picture is right. It's all got to be there. So very difficult to know that it's set up correctly. So that's what people, on the test, the setup is worth like, 2 or 3 points. The picture is worth 1, the antiderivative is worth 1, the evaluation is worth 1. But do you have the right setup? That's a whole different question. All right, find the area bounded by these curves. What's different about this type of problem? Yeah, it doesn't give you any bounds. So therefore, the bounds are going to sit with the intersection. So x squared minus 2x plus 1. What shape is that? It is a parabola. Does anybody know what the y-intercept is? The y-intercept is 1. Does anybody know what the x-intercept is? So this factors to x minus 1 times x minus 1, doesn't it? So that is, it has a double root at 1. So the shape of this parabola looks like this. Calvin, we knew it had a y-intercept at 1 because the constant on the end is 1. And then you have a line, y equals 2x plus 1. Everybody obviously knows what that graph looks like. So if I want to find the area, I'm going to consider the height Yeah, it's a rectangle. So what is the top? What's the bottom? Excellent. Need to find the points of intersection. So that gets to your point, Michael. I can see this one is quite obvious, isn't it? 0. So you're going with the x values, correct? Okay. You see you have that vertical rectangle. The width is dx. That means everything needs to be in terms of x. So we have 0. Our top is 2x plus 1. We're going to minus x squared minus 2x plus 1 dx. I need to find that other bound that sits on top there. So in order to find that other one, I'll set the two equations equal to each other through substitution. X squared minus 2x plus 1 is equal to 2x plus 1. Subtract the 2x over and subtract the 1 over, I get x squared minus 4x is equal to 0. Factor out the x, I get x minus 4. Or 0 and positive 4 are my solutions. Yep, this spot is 0 and this spot is 4. You would have to solve it according to the picture that you've been given. Now I have the integral from 0 to 4. 2x minus negative 2x is 4x. I have a minus x squared, and 1 minus 1 is 0. The antiderivative of 4x. Plug in 4. 4 squared is 16 times 2 is 32. What is 4 cubed? Minus 64 thirds. Find a common denominator. 32 multiplied top and bottom by 3, I get 96 thirds. Minus 64 thirds is 32 thirds. So remember, coming into this year, you knew you didn't even know an ounce of calculus. So to consider solving a problem like this, what is the area bound in between those two things? And then look at how quick work we made of that. That's pretty good stuff. One more example. A lot of people go into that want to be math majors, and they generally make it through Calc 2, Calc 3. The class that takes math majors out of the mix is your real analysis courses or your abstract algebra courses. I had many friends who want to be math majors. They couldn't make it through those courses. And it ended, so. Who? Abstract algebra is a challenging course. So. Yeah. Anyway. All right, here we go. Sine of x and cosine of x over 0 to pi over 4. What does sine look like? Squiggly, good. All right. Let's do some more technical terms. How about a period of 2 pi? How's that? Starts at the middle, as you said, Andrew. Very good. Very good graph there on my part, but oh well. Are we okay with that? How about cosine? That cosine's going to start up here. Let's do that. I want to find the area between the two curves bounded between 0 and pi over 4. Yeah, we kind of hope that pi over 4 is the point of intersection, don't we? Let's verify that it hopefully is the point of intersection. We'll take the two curves, set them equal to each other. We'll see how much you remember from your trig class. I know your trig teacher was a kind of a piece of work, so we'll see. Where is sine of x equal to cosine of x? How do we solve that? Why? Pi over 4 is root of 2 over 2, root of 2 over 2, right? And so you can see that sine and cosine are equal to each other at that spot. If we actually do some equation solving here, When we divide by cosine, what's sine over cosine? Tangent. Where is tangent of x equal to 1? Yeah, if you inverse that, you'll get pi over 4. So yes, in fact, this spot right here where they intersect is pi over 4. So we have our integral. What are our bounds? 0 to pi over 4. Yes, you need to show this work on your test. The integral symbol is a very important thing. It's not optional, okay? What's the function that's on the top? Cosine of x, function on the bottom. Sine of x, dx. There's debate among many AP teachers about whether or not you need to include the parentheses around there. The general understanding is you do not need to include parentheses around there, as though the dx applies to just sine. No, it's just assumed it applies to everything between the dx and the integral symbol. See what I'm saying? Okay, so I think on the AP exam, I think they do actually include the parentheses, but I don't see really even books do that. So, all right, so let's do this. Antiderivative of cosine. Positive sine. Antiderivative of negative sine. Positive cosine. And we're going to evaluate those at pi over 4 and 0. Sine of pi over 4. Root of 2 over 2. Plus cosine of pi over 4. Minus, a lot of people see the 0 and they're just like, well, it'll be 0. No. Sine of 0, cosine of 0. And so we get, stop it. We get, what's the root of 2 over 2 plus the root of 2 over 2? That's the exact answer. Just pretty cool.